For you. This joint work with Moritz Lichter and Manuel Weil from Technical University of Darmstadt. So firstly, I want to introduce a notation for builder dependencies. So for me, a builder is something that maps sources to target files. So we have this builder component in the center, and then I mark requirements of the builder using this dotted arrow, and I mark the files that a builder generates with this spotted arrow. All right, so this builder requires some source files and provides some target files. But a builder can also depend on other builders. So maybe builder requires that builder 2 runs first. So what this talk is about incremental rebuilding. So let's say one of the source files changed. The question we want to answer is, in which order do we need to re-execute the builders to achieve optimal incremental rebuilding that's also sound? So let's take a step back and let's look at what make does. I assume everybody knows make to some extent. So here's a really small make script. We have a make target foogen, and it depends on a Java file, default.java, and it copies that file to another file, foo.java. And we can use this notation to say that, foogen depends on or requires default Java, and it generates a file called foo.java. And here's another make target called food class, and it depends on the foogen target, and it compiles that file. What's the problem with make? Make is incremental, right? The main problem is that the dependencies are fixed in the build script. All of these arrows you see on this image, they're physically represented in the build script on the left-hand side. So what's the consequence of that? Well, firstly, it's really annoying to write all these dependencies there. So what people often do is over-approximation. So you would say, well, my build target depends on all the Java files, and then I compile some of them. So what's the problem with that? So let's take a look here. We have this overbuilder. It depends on foo.java and unused.java, and generates a foo.class file. Now, if the unused Java file changes, we're going to re-execute that builder. But that's not optimal. We rebuild more than is necessary. What's even worse is if you have under-approximation. So here I assume that foo.java imports bar.java, but we only invoke the compiler on foo.java, and the build script only says I depend on foo.java. So it looks like that. So there is this bar.java file, but there's no requirements arrow. So if bar.java changes, we're not going to re-execute the builder, even though foo.class would change. So this is unsound. We rebuild too little. And as I indicated in the beginning, we can fix this problem with make by anticipating all the dependencies our build is going to have. So we can say our builder actually depends on foo and bar.java if foo imports bar. So we get the right build dependency graph, and all the updates happen correctly. So the problem here is it's very fragile, because you're duplicating the dependency information in the build script. So let's say I change the import in foo.java, then I'm back at over or under approximation, unless I update the build script too. Our solution to this problem is to use dynamic dependencies. So if you want to think of a make script, it's basically a make script that doesn't have any dependencies statically. We're only going to discover those dependencies while the builder runs. So we're going to start with a builder that has no environment information whatsoever, and we're just going to start executing it. And this builder is going to tell us what files it requires while it's executing. It's also going to tell us what files it generates. Once the builder finishes running, this dependency graph stabilizes, and we're going to store it and use it for detecting inconsistencies and for detecting when we need to re-execute that builder. Based on this idea, we have developed a build system that's sound and optimal, incremental, and it uses these kind of dynamic dependencies. And this build system is called Pluto, and it has a couple of nice properties. First, it's demand-driven. So the user is telling us what kind of build result he or she expects, and then the build system is going to figure out which builder need to re-execute to provide an up-to-date result. As I just explained, we're using dynamic dependencies. Another feature is that we have semantic file stamps, so we're not necessarily relying on something like timestamps or file hashes, but the user can actually decide what stamps to use. And finally, we support cycles. So there's cycle detection, and you can program your own cycle handling. And last but not least, we have a formal model of our build system, and we have verified that it's indeed sound and optimal incremental, where optimal means that we rebuild exactly those builders that are necessary to produce an up-to-date result, but it also means that we're not going to check the consistency of anything that's not going to end up in the final result of the build. All right, so it's instructive to, again, take a step back, and let's see how make is actually performing incremental builds. And this happens in two phases. So if there is a change, make first produces a schedule of which build targets become inconsistent and need to re-execute. That's the first phase. In the second phase, it's actually going to execute that build schedule. Now, if during the execution, you notice that, oh, actually, I also depend on that, or this dependency is not necessary anymore, then you get these new dependency information. But in make and any other build system that has these kind of static dependencies, there's no way for you to now update the schedule because there's a strict phase separation. The insight, I think the main insight of our work here is that we can interleave the scheduling and the execution. So when in our system we have a change and a build request because it's on demand, then we start to check whether the build request that's of the user actually needs re-execution. And as soon as we discover an inconsistent builder, we immediately execute it. So we don't build a full schedule. As soon as we find anything inconsistent, we immediately execute it. Now, during execution, if you require another build to run, we go back into checking mode so that if this other builder was provided before, we can reuse it. And if this other builder is also inconsistent, we will go again into execution mode of that one. Of course, during checking mode, if one builder requires another one, you stay in this checking mode. I want to explain this algorithm in more detail by walking you through a larger example. So the example I'm going to use is we compiled some Java files, and then we're going to run some benchmarks on top of these Java files, but this is dependent on some configuration file. So this configuration file is going to say which classes, which of the code you actually want to benchmark. Then we're going to generate some LaTeX report, we're going to generate some diagrams, and we're going to compile the LaTeX report into a PDF. All right, so let me translate this description into a dependency graph. A graph that looks like a graph that represents the dependencies after the initial run of the build. So first we have these Java files that we compile. Then we take the result of these Java files, and there's this configuration file on top. It's probably hard to read at the back, but on top of the benchmark node, there's a configuration file that says run A, run B, and run C. And the idea is, if we delete, for example, the row saying run A, and then the benchmark needs re-execution, right, because the configuration changed, but the next iteration we lose this one dependency on a.class, which means that we actually don't need to rebuild a.java if it changes. All right, let me finish this graph. So we take the benchmarking result, it produces CSV. We take this, compile it into a diagram and into the text file, and finally recompile the LaTeX report. All right, so what's really important here is that actually we don't allow arbitrary dependency graphs. That wouldn't be sound and wouldn't be optimal incremental. What we do is we enforce 3 distinct invariants on top of these dependency graphs, and we do this dynamically. So the first invariant that we enforce is every builder kind of stores on the hard drive a summary file so that in the next run we can detect what actually changed. And these summary files may not overlap. And it's actually easy for us, for our system, to automatically ensure that this doesn't happen. The second invariant is that no 2 builders may generate the same file, because then it becomes kind of unclear if this file needs to be rebuilt, which builder to execute. And the third invariant is actually the most interesting one. There may not be any hidden dependencies. So what is a hidden dependency? A hidden dependency occurs if a builder uses a file that was generated by another builder, but the builder that uses the file does not depend on this generating builder. And you can actually not see this yet, but there's also these builder dependencies that I had in the dependency graphs at the beginning. And if you want to use, if the benchmark wants to use the class file, it needs to have a builder dependency on the Java C builder that produced that class file. Because otherwise, if the Java file changes, the benchmarking is not going to notice that. All right, before I mentioned that, Pluto is optimal incremental, and I want to illustrate on top of this example how the rebuilding algorithm actually works. So let's say we have changed the source file a.java. And let's also say the user requires that he wants an up-to-date PDF report of the benchmarking results. So we're going to start down there at the LaTeX builder. And this blue arrow is going to move through this dependency graph, and we're going to check which builders need re-execution. So we start checking the article class file, which happens to be the first source file that this builder depends on. And we notice, well, it didn't change, so that's fine. And then we're going to traverse up the dependency graph. What's important here is, before we're going to go into the report text, which was generated by the report generator, we're going to check whether the report generator itself needs rebuilding. Because if the report generator itself is inconsistent, then it doesn't matter what it produced in the last run. It only matters what it will produce now. So we go up this graph, and the report generator depends on the benchmark. And the benchmark depends on the configuration file. And the configuration file did not change, so that's good. Benchmark also depends on Java C of B, which depends on this source file and generated that file. So we're actually also keeping track whether generated files changed. If a generated file changed, this is also an inconsistency, and the builder needs to re-execute. All right, so the source file of Java C applied to B did not change, and the result did not change. So the whole builder, or the whole build unit, is considered consistent here. All right, then we go to Java C applied to A, which requires a.java. And of course, here we see that a.java did change. So this is inconsistent. And now the important thing happens. Instead of scheduling anything for later, we immediately go into execution mode. So we start executing the Java C builder for A, which is going to read the Java file, produce the class file, and finally, whenever a builder executes, it's going to be consistent after its execution. All right, now we can go back to benchmark, right? We're back in checking mode now. We're still checking benchmark. That was just part of the sub-dependencies. And from benchmark's point of view, now the class file did change, right? Because it was just recompiled. So now the benchmark itself becomes inconsistent, which means we need to re-execute the benchmarking, which is exactly what we want, right? So we're going to do this. I skipped a couple of steps here, but basically at some point we're going to read the class file again. Now we're executing it, so we're updating the stamp that we have for that class file. We're going to produce the CSV file, and finally the execution ends, and we have found a consistent representation of this build unit. All right. The algorithm goes on and will go back to the LaTeX build eventually, but I skipped these steps here. So the interesting question now is, what happens if the benchmark configuration file changes? Because this really provides dynamic information. So we depend on the file, and depending on the content of that file, we install further dependencies. So let's see what happens. So the config file did change. I deleted the line saying run A. And we're currently checking whether benchmark is consistent or whether it needs rebuilding. OK, so we look at the configuration file, which did change. So we immediately go into execution mode for benchmark. OK, so benchmark reads the configuration file. It goes to Java CB, which is still consistent. It produces the CSV file. And we are done. So what just happened is that we didn't even consider to look at a.java because there was no scheduling. We just executed it. And in the current execution, there was no notice of A whatsoever. So this part of the old dependency graph is really unused. And it doesn't matter whether a.java changes or not in the future. We don't depend on it anymore. So this may seem a little ad hoc, I don't know. In our paper, we have the algorithm all spelled out. And we have verified that it's really sound and incremental, meaning where incremental means that you build exactly the right amount of builders, but you also only check the consistency of files that will end up in the final build result. We have implemented Pluto as a Java API, so your build scripts are Java programs. And here's actually the build script for the benchmark. And I'm going to walk you through a couple of the details. So first, it's just Java code. So you write a Java method that implements your builder, which is nice because you can now debug your build scripts easily. But also, while there's a couple of API methods that we provide that are important. So firstly, we provide a method called require. It takes a file and a stamper. And this is how you dynamically install a dependency on some file. What's important here is that this require call can occur within other control structures like an if-then-else or, as shown here, in a for loop. What we're doing here is we pass the configuration file of the benchmark, and then depending on the results of this parsing, we install further dependencies. So here we are installing dependencies on the Java C builder and on the generated class file from that builder. But this really dependent on the content of the configuration file. Finally, there's also another API method that we provide called provide, with which you can say, well, I generated this file. And this is also important not only because we want to detect these inconsistencies, but also we want to detect these hidden dependencies, right? So if you provide something, nobody's allowed to require it unless they require build yourself. All right, so we have evaluated our build system on a build script for SpoofX, which is a tool for building DSLs. And we have re-implemented the ARN script that they used before. Here's some statistics. So the ARN script had 34 targets. We have 23. Maybe what's interesting is that we require about 60% more lines of code than the ARN script. But that's kind of unsurprising, right? Because we didn't focus on designing a DSL or anything. We just provide an API, and we're focusing on the algorithmics of the challenge. There's 60 builder dependencies in our build script. And what's also interesting is we did find 6 hidden dependencies, which means that there may have been scenarios where something changed, but not all the necessary rebuilds occurred. So let's look at the speed-ups that we achieve. So this is all relative to running our build script after everything changed. So in the first line, you see a clean build with our Pluto script. It takes about 30 seconds. And then really depends on what you change in the language definition. If you change nothing, well, okay, you get a speed up of 1,000 something. But if you change the grammar, you still get a speed up of 2. And that's different than changing the editor services or something like that. And the reason is that a lot of other parts of the language definition actually depend on the grammar. So the speed ups kind of reflect the dependencies that you have in the dependency graph anyways. So for us, this was a really nice result. I think we achieved really good speed ups here. So to conclude, I presented an incremental build system called Pluto, which is demand-driven. It used dynamic dependencies to allow you to precisely describe your dependencies and not requiring you to statically over-approximate them. We have semantic file stems, which I didn't have time to talk about, and we also support cycles. And we have a soundness proof. Thank you very much.
We do have some time for questions.
So I'm just curious, if you have a new type of generated file or something like that, do I need to